Hello everyone and welcome to Lesson 6 of the Geometry Summer Course. Today we're going to be covering Proofs Part 2. Assuming you've already seen Proofs Part 1, this is going to be this is the hardest lesson of today, of the summer. And especially the homework. The homework is the hardest homework of the summer by far. And I'm just warning you that right now, so when you do it, you're going to be like, man, this is hard. But it makes sense, because that's what Dan the tutor said would happen. So first we're going to do a quick review of proofs, and basically we're going to be doing proofs all day today. And just as a reminder, what do proofs do? We're proving something. Like for instance, two triangles are congruent, two side lengths are congruent, two angles are congruent. We're proving statements in geometry, basically. And we have this whole column here with statements and reasons. And if you remember, we have a word bank for these reasons. Like for instance, given, which is always first. Definition of congruence, definition of bisect, definition of midpoint, all those are straightforward. Perpendicular lines form right angles. Right angles are congruent. Intersecting lines form vertical angles. Definition of vertical angles. Vertical angles are congruent. All three of those basically saying the same thing. And then finally, the triangle congruence theorems, which I go over again down here. Reflexive property, which is something along the lines of saying AB is congruent to AB, and typically we do this whenever there's an overlap for the triangles. That's when we use the reflexive property. And then the last one is to say CP/CTC, congruent parts of congruent triangles are congruent. That was the theorem that said once you prove that two triangles are congruent, then everything's congruent, not just SSS or AAS or any of these four. Every side, every angle's congruent. That's what that theorem says. And, I don't even think I need to go over these, but we got the four right here, side, 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 angle, angle, side, and angle, side, angle is how we prove two triangles are congruent. So any questions on the stuff from last week? Yes, go ahead.
Hold up. Isn't angle, side, and angle, the same thing?
They're very similar. Let me show you the difference. Here's angle, side, angle, side. And here's angle, side, angle. Angle, side, angle. See, it's slightly different.
Not even close.
Okay, so you're good?
Two angles and one side pretty much mean the same thing.
Yeah, the only thing you have to be careful, remember the one that's not a congruency theorem is side, side, angle. If you have a side, another side, and then an angle, that is not congruent. That is not one of our congruency theorems. That's the only one you got to watch out for. Also, angle is not one either. But basically every other combination is, so that's nice. So now on to the stuff for the new stuff this week. We're going to add a few new reasons to our list. First is the isosceles triangle theorem, which is to say that if you have two angles that are congruent, then automatically the sides are congruent as well. And by the way, the same is true in reverse. If you have the sides are congruent, then automatically these angles are congruent here. So if one is true, both is true. By the way, I'm going to say there's such thing as I know I didn't write it down, but I'll write it down right here. The definition of isosceles triangles. Definition of isosceles triangles. What that basically means is that if two triangles are isosceles, then two sides / angles are congruent. I'll give you a second to write that down. I know it's a lot. And by the way, it's very similar to the isosceles triangle theorem, and you'll see the difference in a problem later on today. Okay, I'm assuming you have this written down. Next, we have the substitution property.
I don't. Thank you.
Okay, I'll slow down. Sorry. Okay, I'm going to keep going. If you need to copy it at the end, I'll just go back.
Well, I'm done anyway.
Okay, next is the substitution property. Substitution property says whenever two things are congruent or equal, you can substitute them in the equation. As the example I have here, x plus y equals z. I also know that x equals b. So in other words, I can replace this x with b, and that's why I can say b plus y equals z. This is going to come in handy, especially when we're adding sides together, and you'll see what I mean. And then last we have the addition and subtraction postulates. These basically say if you add two things together, you can not just add two things together, if you add two line segments together. Like look at this. A plus AB, this right here, plus BC, this right here, equals AC, which is the total. Now I know that seems obvious to you and I, but we still have this addition and subtraction postulate that basically proves it, and we're going to use it for the proof. And then we have the exact same thing with the subtraction postulate, except this one you have to use your brain more. If you have AC, the whole thing, and then you subtract BC, I'll subtract it in red here, what are you left with? You're left with AB. And that's another way of using the subtraction postulate. Any questions on either of those? Okay. So now, for the rest of today, we're going to be doing examples. I think we have like 6 or 7, maybe it's 6 examples to look at today. They're all difficult, and I'm also making it harder because lesson 5 was proofs part 1. This is proofs part 2. You're supposed to be better, theoretically. So anyways, number 1. Given AB is congruent to BC, I'll just mark that real quick. AB congruent to BC. And I also know ADB and angle CDB are both right angles. These angles right there are right angles. I want to prove that the two triangles are congruent, BDA and BDC. So first the givens. I always just copy the information from the given, just like this. And then angle ADB and angle CDB are right angles. Okay, so there's my given. Pretty straightforward. Next, you see the reason is the isosceles triangle theorem. And I already know that these two sides, AB and BC, are congruent. Does anyone want to take a guess as to what two angles are congruent because of the isosceles triangle theorem?
Which two angles?
Yes, because we already have two sides. That means two angles are also congruent. The answer is, go ahead.
B? Is it angle B or angle A and angle C?
It's A and C. And the reason why it's to cross from each of those sides, like you see here. So I'm going to say angle A is congruent to angle C. Okay, so that's it for the two angles. Good. Now I'm saying ADB is congruent to CDB. That's my two right angles. What is the reason for why those two angles are congruent? I'll give you a hint. They're both right angles.
Oh, yeah. Perpendicular lines form right angles.
Close, but no cigar.
Right angles are congruent.
Right angles are congruent. That's the best answer. Right angles are congruent. Okay. And now look at the proof statement. That's going to be the next line. BDA is congruent to BDC. Well, what do I have right now? It looks like I have a side, an angle, and an angle. Side, angle, angle. That's not a congruency theorem. But if I write it backwards, in other words, AAS, which is the same exact thing, that is the congruency theorem. So that's what I'm going to say. Because of AAS, the two triangles are congruent. Any questions on that first one? Okay. The first one was the easy one. Now, number 2. This one will be harder. Given that DF is congruent to EG. So DF, that's this right here, and EG is this one right here. These two things are congruent. It's kind of hard to use the tick marks to say congruent, because just think about it. If I were to say a tick mark right here, I mean, how do I know if I'm talking about EF or DF or DG? It's kind of hard with the tick marks. So whenever I have these with the line segments, what I like to do is I like to draw these, these longer lines. Now I know exactly what I'm talking about here. And then I want to prove that DE is congruent to FG, the two smaller ones at the end. Okay. So first the given, pretty straightforward. DF is congruent to EG. Just copy the given statement, as always. Next, I say EF is congruent to EF. Which reason is that?
Reflexive property, right?
Exactly, it's the reflexive property. And the reason why we would do that is because, honestly, it might be optional, but I see it all the time, so I would say reflexive property. And the reason why we say that is because EF is a part of both DF and EG. I repeat, EF is a part of DF and EG. That's why I'm using the reflexive property. Now, you see here that I have these two things added together equals DF, and FG plus EF equals EG. What's the reason for that? It's going to be the addition postulate.
Wait, what?
The addition postulate says that I can add two line segments together, and that's exactly what I'm doing. I'm saying DE plus EF equals DF. And think about why this makes sense. Let me color it in blue. I'm saying DE plus EF equals the whole thing DF. And then I'm saying EF plus FG equals the whole thing EG. And maybe now you can see it maybe in the picture. Maybe you don't know how to explain it in geometry proofs. But you look in the picture, if you subtract EF from both sides, I mean, you've pretty much got it. You've got DE equals FG. But before we can do that, before we can say subtract EF, you first need to say DE plus EF equals FG plus EF. What is the reason for that? Anyone know? Here's where this is coming from, by the way. DE plus EF is really DF. So really I'm saying DF is congruent to FG plus EF. That's EG. So I'm saying it's congruent to EG. If you notice, that was literally the very first statement. So what am I doing? I'm substituting this for DF, and I'm substituting this for EG. In other words, this is the substitution property. And if you don't see that, that's okay. This is pretty advanced. But I just want you to, at least, I'll say the answer and you can say, oh, that makes sense. Fair enough. And then what am I doing to go from the second to last step to the last step? What's the difference? Because it looks like I'm removing EF. Looks like I'm removing EF. What is the reason for that? That is the subtraction postulate, because I'm subtracting EF from both sides. And after you do that, you've got it. DE is congruent to FG. That's what we were saying from the beginning. So as you can tell, this one looks easy because it's just two line segments. But the proof is like 5 or 6 steps long. Yes, questions?
Can you repeat that again? I wasn't paying attention.
I was just saying that even though this looks easy, because it's literally like 3 line segments, it's still difficult because it's like 5 or 6 steps for the actual proof. Okay, now we're going to go to the next one. I'll admit the next one I kind of mess up a little bit. I'll just tell you this is supposed to go there. In other words, I've already given you the last statement. YZ is congruent to UV. And just cross out that last line. You don't need it, actually. Okay. So first, we're going to rewrite the givens. We got XZ is congruent to XT. Got a lot of givens. We have XT is congruent to TV. And we have XY is congruent to TU. Now let's be clear about what we're saying here. XZ, that's this one right here. We say that's congruent to XT right there. And we also say that XY, wait, I'm sorry, I missed one. XT is congruent to TV. Yeah, that's what I missed. Okay. And then finally, XY, I'll use a different color. XY is congruent to TU, this one right here. And we want to prove that YZ is congruent to UV. In other words, the short one is congruent to the other short one. And again, this looks like it makes sense because everything's symmetrical. But that's not enough for a proof to just say it looks symmetrical. We have to use these reasons. Now, one thing I do want to tell you, maybe you realize right away that because ZX, XT, and TV are all congruent to each other, that must mean that ZX on the left is congruent to VT on the right. And as a matter of fact, that's literally the first statement I give. I say that those two are congruent. But why are they congruent? Can someone tell me?
Is it because of the addition postulate or something?
You're close. It's not addition because addition would be if I was, let's say, adding ZY and YX. This is the other new one we learned today. It's the substitution postulate. Or not postulate, substitution property. Substitution property. And why is it substitution? Because I'm substituting, look here, XZ and XT. I'm substituting, well, remember, XZ and ZX are the same thing. I don't know why I wrote it backwards. But XZ is congruent to XT. XT is congruent to TV. Therefore, XZ is congruent to TV. And I know I have it backwards, but I think it's pretty clear based on the picture. Okay, and it's funny because I literally give the rest of this, but I do want to point something out, at least in terms of the process. In terms of the process, when we have YZ is congruent to ZX minus YX, notice I'm subtracting. YZ, the short one, is equal to ZX, the long one, minus YX. And that makes sense. And then you'll notice I have another statement. It's UV is congruent to VT minus UT. I would then ask you the question, am I allowed to put two statements at once? And the answer is yes, as long as they share the same reason. You notice they both use the subtraction postulate. I even say the word twice here. You don't have to say the word twice. I'm just telling you that as a hint, because in the next problem, you might not have the two statements I have here, okay? But I'm going to give you a hint, because in the reason I'll say twice. You don't actually have to write twice. That's me giving you a hint. And then the last step is, it's just the substitution property. Again, you're substituting basically YZ with this right here, and you're substituting UV with this right here. And again, we said all of these parts individually are congruent. What do I mean by that? I said YX is congruent to UT. I said ZX is congruent to VT. So that must mean that YZ is congruent to UV. Any questions there? Okay. Number 4 has a lot of fill in the blanks, so it's definitely going to be harder. Okay, looks like the given is ML is congruent to LK. So ML congruent to LK. That's given. Also is given triangle JKL and triangle MNL are isosceles. So after I rewrite all the givens, it looks like the first statement I say, well actually first let me mark this on the diagram. I said ML and LK are congruent, okay. Then the next thing I say is ML is congruent to NL. I'm saying ML right here, congruent to NL right there. I also say JL is congruent to LK, so these are congruent. Why is that true? It's true because of the definition of isosceles. Yep, definition of isosceles triangles. Because isosceles triangles share either two sides or two angles. In this case, I gave you a side, so, I mean, remember, both are true. The sides and the angles are both congruent. But as you can see, I first said the sides are congruent. Now, the next fill in the blank, what do you think that's going to be about? Take a wild guess. It has to do with isosceles triangles.
Is it bisectors this time?
Not bisector, and the reason why. I know it looks like a bisector, but here's why I don't say it. It doesn't say it in the problem, and so I don't want to say it right now. In other words, a lot of the problems we looked at last week had bisect or midpoint. Yeah, it said it in like the given. That's why we would say it back then. But now, it doesn't say bisect or midpoint anywhere, so I don't want to say it now. Instead, I want to say that these angles are congruent and these angles are congruent.
Right angles are congruent.
They're not right angles, but they are congruent. I'm saying angle J is congruent to angle K, and I'm also saying angle M is congruent to angle N. And the reason why is because of the isosceles triangle theorem. Now you may be wondering, what's the difference between the two reasons, because they sound almost identical. I'll tell you the difference.
What reasons?
Definition of isosceles triangles and isosceles triangle theorem. I just wrote triangle. That's terrible. That's theorem at the end. Sorry. Yeah, these two reasons are different. The first one, definition of isosceles triangles, just says if I tell you they're isosceles, then two sides or two angles are congruent. The isosceles triangle theorem says that you've got two sides, then these two angles are congruent. That's what the isosceles triangle theorem says. Okay, next you see definition of vertical angles. What do you think I'm going to say this time? Which two angles are vertical?
J and N are vertical angles, along with K and M are vertical angles.
Incorrect, but thank you for trying. The reason why is because vertical angles always happen at intersecting lines. The only lines that are intersecting here are L right here. So L and the other L are both vertical angles, and that means they're congruent. Go ahead. I would say angle JLK is congruent to angle MLN. And again, that's because of the definition of vertical angles. You could also say vertical angles are congruent, because they're basically the same thing. And now it's funny because the next line, triangle MNL, is congruent to triangle JKL. I mean, you have your pick here. In other words, I have an angle aside and another angle. I also have angle side. I have side angle side. Yeah, I've got like 3 different theorems. I didn't need to go crazy like this, but yeah, I wanted to. So literally any 3 of these would work. I'll just say ASA, doesn't matter. But remember, there's more than one for this one.
How does side angle side work? I don't get it.
Yeah, you've got this side, this angle, this side.
Oh.
Yep. And then last, we want to say side JK is congruent to side MN. And how do I know? That's the prove statement. You better end with the prove statement, or else what are you doing?
CPCTC.
Thank you. That's correct. CPCTC. That's the theorem that says once you prove the triangles are congruent, literally everything else is congruent. Excellent. And that's going to do it for that problem. Any questions? Okay. 3 more to go. These are the hardest ones coming up. Number 5. Given DCO is congruent to ABO, let me mark that. DCO, that angle right there, is congruent to ABO. That's this angle right here. Then I say that side AC is congruent to BD. So AC, BD, right there. And then I say angle ACO, right there, is congruent to DBO. DBO, that's this one right here. Okay, so that's all we know right now. And I have a feeling we're going to be doing a lot of stuff coming up. So the first thing I'm going to say is for the statements. Can someone tell me what the first statement will be?
Given.
Yes, the first statement is always the given. We have 3 givens here. Angle DCO, congruent to angle ABO. We have AC is congruent to BD. And then lastly, we have angle ACO is congruent to DBO. Any questions there?
No.
Okay.
But
Next.
Can you wait?
Yes, sorry. Yeah, there's a lot of stuff to write there. No, I'll admit there's a lot of stuff to write there. For those of you watching the video, just fast forward. Or maybe watch it in slow motion if you want to really make it exciting. Okay, next we...
Okay, never mind.
Okay, next we have the statement, or sorry, the reason is definition of vertical angles twice. And then can someone other than Shronik tell me what the statement would be? Sorry, Shronik, you've been answering every time.
Is it angle AOB is congruent to angle COD, and angle AOC is congruent to angle BOD?
You're exactly right. So let's mark these. By the way, this is crazy because this is going to be like 4 tick marks because I've already used 1 and 2. So I'm going to say what you just said. Angle AOB is congruent to angle COD. And then the other one, this one right here, will say angle COA is congruent to angle DOB. And if you don't feel like doing the 4 tick marks, for instance, because you know it's confusing, well, you can do whatever you want. Like, for instance, if you want to, you can say 1 mark with a line through it, and that at least is different, so it's a way of, distinguishing it from the other angles, because this gets really confusing. Okay, anyway, that's correct. Next, we need to say triangle ACO is congruent to triangle DBO. Can someone tell me the reason why? It's because I now have an angle here, and a side here, and then an angle here, side here. It's AAS. AAS. Okay, good. Next, it looks like the reason is CPCTC. This one's not obvious. And let me tell you why. Because there's a lot of different things you can say are congruent right now. For instance, I could say this angle's congruent. I can say this side is congruent. I can say this side is congruent. But there's only one, I would say, correct answer. And before you even say what this statement is, and guess, because it would be a guess right now, just remember the prove statement, the last one, triangle DCO is congruent to triangle ABO. Let's go ahead and look at these 2 triangles real quick. I'm going to erase some of my circles. It's getting too cluttered. Go ahead.
Wait, you wrote it at the last box?
Remember, the last box is always the proof statement. So I'm saying I actually don't know what goes here yet. I have to think about it. But I do know what goes in the last box. So I'm going to kind of retrace my steps, if you think of it like that. So I'm saying this triangle here, as my proof statement, is congruent to this triangle down here. And it looks like I already have this angle, and I have this angle and this angle. In other words, I have 2 angles. I just need 1 more side to be congruent, and then I've basically got my congruency theorem. So, would anyone like to guess as to which one I'm going to say?
You need 1 more side?
Yeah, because right now I have angle, and that's not a congruency theorem. I either need AAS or ASA. So what I'm going to say is, I'm going to say this side right here is congruent to that side right there, because now I've got angle, side, angle.
Angle CO is congruent to angle line. CO is congruent to line BO.
Yeah, that's right. CO is congruent to BO. And that's because of CPCTC. And now I've got the triangles are congruent, and the reason is ASA. Now here's a fun fact to you. Depending on who your teacher is, you might even be doing all of these proofs from scratch. In other words, I don't even give you any of the statements or the reasons. However, I think that'd be too cruel. Typically, you're going to spend probably 2 months on proofs when you're actually in geometry, and it's really brutal. So my advice to you is basically the sooner you can remember these reasons and become familiar with all this different stuff we're learning about, the sooner you're going to master proofs. Because believe me, these are hard. Even I probably got some of these wrong, or maybe at least didn't do it the most efficient way possible. And that's fine. Like, I'm not going to pretend I'm perfect at this, but certainly the way we're doing it today is good. Okay, next. Given RUS is isosceles, that's this one in the middle, and angle QRS, where's QRS? That's this one right here, the big one, is congruent to TSR, that's this one right here. Remember, that is not a right angle. I cannot say it's a right angle because nowhere does it say it's perpendicular, nowhere does it say it's a right angle. It's not a right angle, but they are congruent, and that's all I care about. And then the next line, angle URS, this one right here, I'll put 2 tally marks, is congruent to USR. Again, I'll give 2 tally marks. And I need to prove QU is congruent to TU. Okay. So, first things first, the givens. Triangle RUS is isosceles. Angle QRS is congruent to angle TSR. And then angle URS is congruent to angle USR. And the reason for that, again, is the given. Okay, so as you're writing this, also think about what we're going to be doing next. Because it looks like RS is congruent to RS. Any ideas?
Reflexive property.
Exactly. And tell me, why do you think I'm going to be using the reflexive property? It's because when do I use reflexive? It's when I have overlapping things. I've got 2 overlapping triangles here. I think a good...
overlapped.
What'd you say?
So line RS is overlapped between 2 triangles.
Exactly.
Between triangle QRS and triangle TRS and triangle URS. 3 triangles are overlapping.
Yes, exactly. And then what I'm going to do is, I think a good strategy, I'm going to split up these 2 triangles, QRS, and the other triangle, TSR, because it's going to be easier for me to look at this if it's not like 3 things touching each other. It's really confusing. So anyways, I would say that this angle S is like the small one with the 2 tally marks. This angle R also has the 2 tally marks. This big angle R is the 1 tally mark. This big angle S is the 1 tally mark. And then we just said RS is congruent to RS, so RS and RS. Now it's funny because you probably already see angle side angle for these 2 triangles. And that's true. But before we do that, it looks like the next reason is the isosceles triangle theorem. And the isosceles triangle theorem is not about QRS or TSR. Why not? Because remember what I said in the given. Triangle RUS is the isosceles. So how am I going to use the isosceles triangle theorem here? The answer is you already have the angles are congruent, so that means the sides must be congruent. And I'm not saying the whole side, I'm just saying RU and US. RU must be congruent to US, and the reason why is because of the isosceles triangle theorem. And then next, we say the triangles are congruent, RST and SRQ. We actually could have said this a step earlier, but what's the reason why? Remember we just said this a minute ago. It was angle side angle. And you can see that when we have the 2 triangles written out separately. So now we got the 2 triangles are congruent. And the very next statement is QS. This long thing right here is congruent to TR. This long thing right there. What is the reason for that?
They do cross U, right?
Oh, that is true, but I don't care. And why don't I care? It's because CPCTC is the reason why. In other words, look at QS right here. QS is technically this guy right here, and RT is this guy right here. So that's CPCTC. And remember, I need to prove... Oh, and by the way, there is a line missing here, so we can add one real quick. But I need to prove that QU is congruent to TU. And remember, the last statement is always your your proof statement. So who can tell me what the missing statement is? It probably has something to do with QS and RU and US and TR, because that's the only thing we haven't related yet. The answer is the subtraction postulate. I'll tell you that's the reason. Can someone tell me the statement then?
Does it have something to do with QS and TR, or just the QRS?
It has to do with the
QS plus US or something.
Well, yeah, it's close to that, except it's not plus, it's subtraction. It's
QS
QU.
minus US. QU minus US, right?
So, it's QU is congruent to the whole thing QS minus US. Is that what you said?
Yes.
Now, obviously, couldn't you say QU plus US is congruent to QS? Yes, you can say that. Why didn't I say that? Because what am I trying to prove? I'm trying to prove QU. So I want QU to be on one side and then the subtraction to be on the other side. And by the way, we're going to do the same thing. This is actually 2 lines. I definitely didn't give myself enough room. Hopefully you did give yourself enough room. But the other one is basically the same thing. TU is congruent to TR minus UR. So that's the subtraction property. And then somehow I go from that step to saying QU is congruent to TU. How on earth do I do that?
Substitution property.
Shronik, I heard your answer. Any other you said something else?
Oops.
Go ahead, other person.
I was going to say the substitution property.
Okay, good, because you're both right. I just was curious if you said the same thing. It is the substitution property. And I think you see why now, but let me just explain it again, just in case, for those of you who don't understand. It's because, what are we substituting? We're substituting this, QS and US, and we're substituting this, TR and UR. Why do I get to substitute that? Because remember, we know for a fact this is congruent to that, and we also know that the whole thing is congruent to the other whole thing. And because we know everything else is congruent, and we just did subtraction, the only thing left to say is substitute it because everything else is congruent. Any questions on number 6? If not, then there's only one more left. It's number 7, and this is a monster. A monster of a proof. I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. So we'll be here for about 10 minutes. But then this is the last one, so it's nice. Also, one thing I do want to say for the homework, I think I go a little bit overboard with some of the addition and subtraction postulates. And you'll see why with this one. This one's kind of a little overboard, I'll admit. But I think it's all necessary. I'm not actually sure. Number 7, the givens are G and K are right angles. I'll mark that. G and K are right angles. GLH, that's this one here, is congruent to KMJ. That's this one right here. I know HI is congruent to IJ, and then I know IL is congruent to IM. And all of that I am now going to write as my givens. Angle G and angle K are right angles. I know that GLH is congruent to angle KMJ. I know that HI is congruent to JI. And finally, I know IL is congruent to IM. And all of that is because of the given. You'll notice my handwriting is terrible. I know, but whatever. This is good. And so then the first statement we have is angle G and angle K. Why are they congruent?
Right angles are congruent.
Right angles are congruent. Easy peasy. That's probably the only easy part to this entire proof. Right angles are congruent. Okay, now you can see here, I kind of give you a hint. I say the addition postulate twice. It probably has something to do with HI, IL, and JI, and IM. Can anyone tell me what they think? Well, I would say that HL, the entire thing, is congruent to HI plus IL. And again, that's because of the addition postulate. And then we're just going to do the same thing for the other diagonal. JM is congruent to IM plus JI. And again, that's the addition postulate. Now for the next one, I would accept either the addition postulate. I would also accept the substitution property. I'll put this in parentheses. I think substitution property is also correct. And the reason why is because we're saying HI and IL, in other words this one and this one, is congruent to IM plus IJ, this one and this one. And the reason why is because we know all four things are congruent individually, as you can see by my tick marks, which means they must all be true together, added together. So I would accept either one. But then the next statement, you need to tell me why. HL is congruent to JM, the two long diagonals. Can anyone tell me? This, for sure, is the substitution property. Yep.
Absolutely.
Because we're substituting the two individual statements with just one statement. And the next line is saying the triangles are congruent. So before I actually say the triangles are congruent, let me draw them separately again because I think that helped last time. So we got H, G, and L. And then on the other one we got M, J, and K like this. We know that G is congruent to K. We know that L is congruent to M. And now we just said HL is congruent to MJ. Which means it looks like I have an angle, and a side. And that's why the triangles are congruent. Okay. Now I'm going to take a pause and ask myself, what am I trying to prove again? Looks like I'm trying to prove GM and LK. That's the two little guys at the bottom. Okay. So now the next reason is CPCTC. Who thinks they know what the statement is? Go ahead.
I think I lost it. Is it HG congruent to JK?
Why?
Or...
I mean, you're not wrong. They are congruent. But that's not going to help me because you see GM and LK, the thing I'm trying to prove is on the bottom. I'm going to say GL is congruent to MK because they're both on the bottom. That's going to help me get there.
Yeah, you're right.
So GL is congruent to MK because of CPCTC. And then we see the next reason is the subtraction postulate again twice. You don't have to say twice. I'm just saying twice to help you think about it. What do we think the subtraction is going to be?
Would it be like GL minus ML equals GM?
GL minus ML congruent to GM. Is that what you said?
Yeah.
Exactly. And then we're going to do the same thing with the other one. We're going to say, go ahead.
MK minus LM equals LK.
Exactly. MK minus ML congruent to LK. Yep. If you want to, you can even use a reflexive property on the ML. You'll notice I didn't do that this time. I think it's optional in this case. It's kind of hard to say whether it's optional or not. When in doubt, you can just throw an extra line in there. It doesn't hurt. I'm going to tell you actually the next line, that's like kind of a, I don't know if it's a typo or not, but I think I just did too much. It's not necessary. I'm going to cross it out. You don't need it. And then the very last line is GM is congruent to LK, the thing I want to prove, and what's the reason? I think you all know it at this point.
Substitution.
Exactly, it's substitution. Substitution property. That's why the two lines are congruent, because you're substituting in the subtraction, and the reason why you can do that is because everything is congruent to each other. And that's it. That's it for this homework. Not homework, the lesson. Again, this was the worst one. It's over. I mean, not for you. You still have to do the homework. But once the homework's over for you, then it's over. And next week we're going to be covering, oh gosh, I forget what lesson 7 is. I forget. Yes, question.
Wait, when did this geometry course end again? Because I don't remember.
Yes, there's 8 lessons total, so we're 75% of the way done.
So wait, if we get to lesson 8, and once we do the homework, we have to come back again?
Oh, no, you're done. I'm never going to see your face again. Although I will admit, I'm thinking of doing an SAT course at some point. That one probably wouldn't be free. But if you ever want to see me again and you're looking for SAT help or even just tutoring help in general in geometry during the school year, let me know. I'd be more than happy to help you. That, of course, will not be free. But at least with these summer courses, I'm doing it for free out of the goodness of my heart. And really, I'm just hoping that each of your parents will write something nice about me on Facebook. That's the real hope.
Okay.
So thank you all for attending. I'll see you guys next week. And if you have any more questions, just let me know. Bye-bye, bye-bye, bye-bye.